In this module, we will be talking about another discrete probability distribution, which is known as the Poisson distribution. Sometimes our interest is in knowing the number of events occurring in a specific period of time or in a space or specific area of volume. That could be number of death claims received per day by an insurance company, or it could be number of families with those have experienced the child mortality. It could also be number of alpha particles emitted from a radioactive source during a given period of time. In all these three various examples, we are more interested in knowing that in certain time and in certain space, how many time an event has been occurring. Such type of the discrete distributions can be discussed by using the Poisson probability distribution. Poisson probability distribution is named after a French mathematician, Simon Denis Poisson. There are a few characteristics of a Poisson random variable. That if we say that x is our event of interest, then x will be the number of times a certain event occurs during a given unit of time, or it could be in a given area. Then the probability that event occurs in a given unit of time is the same for all the units. Moreover, the number of events that occur in one unit of time is independent of the number of events that occur in another unit, as well as there is a certain value of mean or expected rate, which is denoted by lambda. In some instances, people also denote it by mu or some other notation. But here, we will use lambda as the average number of time our event of interest happens. So, let's say that x is our random variable that follows the Poisson distribution. Therefore, we can call it that it's a Poisson random variable, where this Poisson random variable with parameter lambda, which is the average, can be translated into the probability mass function for the Poisson probability distribution, which is given by lambda to the power x divided by x factorial, which is multiplied by e to the power minus lambda, when x can possibly take values from 0, 1, 2 and onwards. You might notice that in binomial distribution, the range of the values of x was from 0 to n, where n was fixed. But in Poisson distribution, there is no upper bound to the possible values of x. The values of x ranges from 0 up till infinity. Here, lambda is the average number of events per interval, where e is the number 2.71828. It's Euler's number, which is the base of the natural logarithm. So the Poisson process generates a Poisson distribution, which is characterized by the following three traits. The first one is that outcome of the Poisson process should be a discrete outcome, and the number of successes in any interval are independent of the number of successes in any other interval. And lastly, the probability of two or more successes over a sufficiently small interval is essentially 0. Here are the distribution of the Poisson random variable with different values of the mean. As I said, mu is the same as lambda. So it's just the way we denote it, but they both mean the same. That this is the average number of the possible x's that can happen in a given time and space. So you will notice the different shapes for the different values of mu. In binomial distribution, there were two parameters, n and p. But in Poisson distribution, there is only one parameter, which is lambda, or you can call it mu. Let's take an example to find out the probability using the Poisson distribution, where we have some event that occurs very rarely. Like in this example, it happens on average 12 incidents per year in Norway. We got to find out the probability that in the next year, among patients receiving the prescribed treatment, exactly 3 will experience that event of interest. So this probability can be obtained by probability of x is equals to 3 e to the power minus 12, which is the average. 12 to the power 3 divided by 3 factorial, and it gives the value to be 0.00177. Continuing with the same example, if we are interested in knowing that what's the probability that at least 3 patients in the next year will experience the event of interest if the same treatment is administered with anesthesia, you might notice that here it asks for the probability that at least 3 patients, at least we'll talk about come as come, which means something that's minimum and there is no upper bound. It can happen any number of times. So when you say at least 3, the event can happen 3 times, it can happen 4 times, or even beyond. But since we do not know what's the upper bound of a random variable x, which is Poisson random variable that can take, we probably will not be able to find the exact probability. Maybe by using certain algorithms, we can, but not manually. So in that situation, we will use a complementary rule of the probability. Since we know that lower bound of the probability of the possible values of the random variable that's Poisson distributed is 0. So at least 3 can be complemented by less than equals to 2, which can be obtained by the probability of x greater than equals to 3 is equals to 1 minus probability x less than equals to 2. And probability x less than equals to 2 can further be defined as the probability of x is equals to 0, probability of x is equals to 1, and probability of x is equals to 2. Using the probability mass function, we obtained the various probabilities, and when we added all these probabilities and used the complementary rule, the final answer turned out to be 0.99947775, which is a pretty huge probability. So this gives us that there are 99.94% chances that there will be at least 3 patients in the next year who will experience the event of interest if the specific treatment is applied to them. Poisson distribution is often used as an approximation for the binomial probabilities, especially when n is large and p is too small. The rule of thumb is that when n is more than equals to 100, or np is less than 10, then the binomial, the Poisson distribution can be approximated to the binomial probability distribution. Let's look at this example, where we can see that as this in binomial distribution, p goes larger and lambda also increases, the distribution is becoming more and more symmetric. This shows the relationship between the different various parameters of the binomial distribution and the Poisson distribution. So the Poisson distribution is important because it is often used for rare events. It's the most appropriate distribution when we are studying some rare phenomena.